Hello and welcome to Reading Table I. Make sure you have Table I near you so that you're able to reference it as you're doing these notes. Table I tells you your heats of reaction for various reactions at quote-unquote normal lab conditions. What I mean by this, so these are just set conditions, not actually STP, it's a little bit warmer than that, but these conditions are pretty standard lab conditions. If you change these conditions a little bit, it would affect your delta H. So, we're just always assuming that we're at those particular conditions. So what this table is actually telling us is the amount of energy released or absorbed by a reaction. In other words, the net energy or the delta H. Remember, delta H means heats of reaction or net energy change. The unit for delta H is kilojoules. So you remember talking about joules before, nothing new here. Very often these are also expressed in kilojoules per mole. On this particular table, they're just in kilojoules. Whenever we have a negative delta H, remember that means that this energy is being released in this exothermic reaction. Whenever we have a positive delta H, we're talking about an endothermic reaction where energy is absorbed. And what's really nice about this table, if you look down in the way very bottom, there's an asterisk, and it actually reminds you that negative delta H is talking about an exothermic reaction. So if you're afraid you're going to get that backwards, you do have a place you can look that up. So if we want to figure out which energy or which reaction gives off the most heat, we have to find one with the largest value for delta H. And that value, in order to talk about giving off heat, has to be negative. The reaction that does this is the combustion of octane. And you'll notice that has a delta H value of 10,943 kilojoules. So obviously octane is a component of fuel, and you can see why. The reaction that gives off gives off the least heat is the dissociation of sodium hydroxide. That's about a little bit up from the bottom, maybe about 6 up from the bottom. And that's got a value of negative 44.51 kilojoules, which is the smallest negative number. The reaction that absorbs the most heat, if you look for that one, is going to be your largest positive value, which is formation of ethine. Oops, a little organic review for you there, C2H2. And it has a value of positive 227.4 kilojoules. Your reaction that absorbs the least heat is the dissociation of sodium chloride, which only absorbs 3.88 kilojoules per mole of sodium chloride. This ties into our making of ice cream. Sodium chloride, in addition to lowering the freezing point, absorbs heat when it dissociates. So when you felt your ice cream mixture get really, really cold, or your ice salt mixture get really, really cold, that's because the sodium chloride was requiring heat and pulling down the temperature of that water. So if we look at this table, and you find down here the dissociation of sodium chloride. So we want to know if 5 moles of sodium chloride is dissociated into ions, how much heat is absorbed or released. So the first thing we're going to do is we're going to find the dissociation of NH4Cl, and it's got a value of 14.78 kilojoules. The reaction as written is for dissociating 1 mole of sodium chloride, and we are going to go ahead and dissociate 5 moles. So we're going to multiply that by 5, which gives us a delta H, a total delta H of 73.9, and that means energy is being absorbed because this is positive. And that is in kilojoules, of course. Number 2, formation of 1 mole of liquid water, how much heat is absorbed or released. So find the reaction where liquid water is formed. And when you find that, you'll see you have a delta H of negative 571.6 kilojoules. And that's actually in the formation of 2 moles. You're making 2 moles of water in that reaction. So if we only wanted to make 1 mole, we'd divide that by 2. And we get negative 285.8 kilojoules of energy. And that's negative, so this is being released. Number 3, we're going to add energy terms to the following equations. So first thing we do is we find the reaction on table I. Formation of aluminum oxide has a delta H value. I'll write that right here. Its delta H is negative 3351 kilojoules. So this is exothermic. Now, in a reaction, we never write negatives. So to show that this has a negative delta H, we want to show it's exothermic, we're going to put the energy on the product side. We do put a positive sign with it because the fact that this is a negative is really a sign convention. It's not really a negative amount of energy. That energy doesn't get sucked into a black hole. It's just given off. So, we're never allowed in a chemical equation to write a subtraction sign or a negative. So we just make sure that we get that energy term on our product side. When we're looking at the formation of NO2, if we look up our delta H value for that reaction, it's positive 66.4 kilojoules. So since this is positive, this is an endothermic reaction. So we're gonna, I always run out of room for my kilojoules. So this is going to be on our reactant side. And people ask me sometimes, like, what if you snuck it in right there? If you're able to fit it there, that's fine, as long as it's on the left side of the arrow. That's what's important here. And same over here, this has to be on the right side of the arrow. If we're going to sketch a potential energy diagram for a reaction, so this would also involve understanding if we have a exo or endothermic reaction. So the formation of C2H6, it has a delta H value of, delta H value of negative 84.0 kilojoules. So if we were going to sketch a potential energy diagram for this, and I'm not going to put any values on here, but this is an exothermic reaction, so I'm going to start here and I'm going to end lower. Technically, that 84 is the difference right here. So it's that delta H value right there. However, you don't really need to worry about showing specific values. Usually with these, just being able to recognize that because that's a negative value, this is exothermic and ends lower. Last thing we're going to wrap up on this video is the idea of randomness, entropy, and natural tendency of systems. So entropy is the measure of the randomness or disorder in a system. The law of disorder says that systems in nature tend toward, I guess 2 is okay, tend toward or to disorder or chaos. This makes sense. If you don't ever clean your room, it'll become disastrous. Many of your binders are disastrous. If there were no laws or rules in the road, people would run red lights. It would be disastrous. So chaos is what happens when you don't control things. This is actually going to decide whether or not a chemical reaction will happen. And this ties into something called kinetics, which is what we're talking about, and a little bit of what we call thermodynamics. There's a balance between energetics and entropy in a reaction, okay? And this balance is really, really important. Systems in nature want to give their energy away. So it's considered energetically favorable to be an exothermic reaction. If you think about if you took a hot mug of coffee and you set it down, that heat would dissipate or go away into the surroundings. Systems in nature also want to get more random. If you put some salt into water, it will dissolve. You stir it to help it along, but naturally it will begin to dissociate and dissolve and increase the randomness in that solution. So I like to call this lazy, but crazy. Sounds sort of dumb, but what's happening here is you want to give your energy away. So go to a low energy state by giving your energy away. But you still want to be random. Like you want to run around and be crazy. So it's kind of like if your parents went out of town, you'd let the house be really, really messy and chaotic and random, because you'd just be laying around on the couch, giving all your energy away, being very, very lazy. So systems in nature are going to tend toward lower energy states, but they're also going to tend to be more disordered.